Hi class, in these notes we're going to be talking about passive transport. So passive transport is just like it sounds. It does not take energy, and it is something that happens just naturally, so things move passively, it doesn't need an energy force behind it. As opposed to active transport that does need energy. But we're not talking about active transport in these notes, we're just talking about passive transport. So let me turn get my eraser to work here. Page. So first of all, just some definitions that I want to go over. I didn't put these on your target practice because they're just kind of for this context that I want you to know them. So first of all, what is this? This whole thing is a solution. So solution is the dissolved substance in the fluid that forms a particular solution. The solvent is the liquid. For us, the solvent will always be water. So it's always dissolved in water as opposed to any other liquid like oil, for example. So solvent is going to be water in all of our scenarios here. And then the solute is just the solid thing that's dissolved in it. So for example, if this were like a salt solution, then these would be salt molecules that are right here in orange, and then everything else is water that's in it. So we're going to be talking about solute concentration. So that's the amount of stuff that's dissolved in it. So for example, if you have a cup of water and you were to dissolve a tablespoon of salt in it, that would be a whole lot different than if you did like a quarter cup in it. So we're talking about different amounts of solute and how molecules behave when they're in a solution like that. Now, just in general, molecules want to bounce off of each other and move apart from each other. So if you were to spray like air freshener in the air, for example, you'd have a high concentration of air freshener molecules right outside of the can that you just sprayed. They're going to be bouncing off each other and eventually spreading out. So if you've ever played pool, when you hit the cue ball into the rest of the balls, then they kind of bounce off each other and move around and bounce off other things as well that give them this like random movement. And that's what we're going to see as well in all molecules. So molecules in the air around us are always in motion. But when you have a whole big concentration of them in one area, they're going to bounce into each other accidentally, of course, more and then spread out. So in general, the term diffusion is referring to moving from where there's more into where there's less until equilibrium is reached. So like in this scenario right here, we can see a whole bunch of the red molecules here, which is our solute. So maybe this is salt here. And they're going to bounce off each other until they're evenly spread out like this picture right here. Now, that does not mean that once they spread out that they no longer move. They are still moving around and such, but in general, they're going to stay in pretty much equilibrium. They would take a force or energy to make them go to cluster together. So in general, they're going to stay all spread out like that. Now, if we were to take it, like spin it really, really fast around itself, then we're going to see the heavy stuff fall to the bottom. But again, that would take energy to do so. So we're talking about passive transport, so how molecules naturally behave without any outside energy inputting into the system. So we're going to see the solute spread out until it reaches a general equilibrium right here. And they call this moving down the concentration gradient. So in this first picture right here, we have a concentration gradient because we have a high concentration of solute molecules here, and we have a low concentration of solute molecules here and here and here. So what's going to happen, they're going to bounce off each other and they are going to spread out. And they call that moving down the concentration gradient. So that's just in general how molecules move. Here's a different picture of kind of the same concept. We can see our solute is right here. So maybe we'll say this is sugar in this one. So these green dots are our sugar molecules. We have a high concentration of them here. We have a low concentration of them here. So they're going to bounce off each other until they spread out and form an equilibrium. So again, they're moving from a high to a low concentration, and that is moving down a concentration gradient. I kind of think of it as like a slide, and you have a ball on a slide, and it's going to move down that gradient from where there's more to where there's less. So this is a video. It's just a real short clip that I'm going to show you here in a second. In this, they have an artificial membrane. So this is supposed to be a part of the cell membrane right here. These rectangles that are here that I'm outlining in bluish purplish. So this is the cell membrane. And you can see you have a lot of molecules over here on this side. So it's high concentration over here. There's a low concentration over here. So what are molecules naturally going to want to do? They're going to want to go in this direction. They're going to want to go from where there's more to where there is less. However, notice that there are holes in the membrane that I drew my arrows through. Now, luckily for us, these molecules are really small, so they're going to fit through the holes size-wise. So in order for things to cross over a membrane, it has to fit size-wise. It has to be able to fit through it. If it's too big, it can't cross. And it also has to be uncharged as well. So things that are charged are going to get stuck. They're going to get stuck here to it because remember, the phospholipid bilayer is also charged, so it's going to get stuck here. It's going to be difficult to cross. So I'm going to show you the membrane, this video, and I want you to pay attention. Just pick a couple individual molecules and just watch what happens. Notice that their movement is random because remember, there's no input of energy. There's no wind blowing, there's no flow. It's randomly how they bump off of each other. Random motion. Now it's not going to run super long in this video, but if it did run for the full time, we would see that both sides would end up having a pretty even distribution. It would go into equilibrium is what would happen. So we can apply this to a membrane. So here in this picture here, there's just a lipid bilayer. So remember that the cell membrane has these phospholipid molecules that are in it, right here. Oh no, I started something else. It has these phospholipid molecules that are in it right here. Remember, a phospholipid molecule has hydrophilic head. So this is where it loves water and has hydrophobic tails. Here it does not like water. And it doesn't like water because water is charged and the tails are not charged. Now, in this picture, they're only showing the lipid bilayer as part of the cell membrane. Remember that the cell membrane also has proteins that can act like bridges to allow things to go in and out of the cell as well. So in this picture, all they're showing is the lipid bilayer. Now remember, this loves water here, the heads love water, and the tails don't. So things that are charged have a difficult time passing. So if it has a positive or a negative charge, it is a difficult time passing. Some things can pass slowly and some things can't. So in order for things to cross, like these molecules here are crossing over here, they're moving from a high concentration to a low concentration. So they are crossing in this direction. If they're able to cross, then that must mean that they are small. In order to be able to fit, they kind of squeeze in between the molecules here. And they have to be nonpolar, so which means uncharged. Now, there is an exception. So small and polar things like water can actually cross. It just does so very slowly there. So, but things that can freely cross, like you're seeing in this picture right here, are small and nonpolar. So like in this example, this could be glucose. So a very simple type of sugar. A couple of more terms to talk about here. So we're talking about a difference in concentrations. The purple dots in these pictures are the solute. So we're focusing on the solute, the solid that's dissolved. And we'll pretend it's salt or sugar. Let's do sugar, because sugar can freely cross. In yellow is our cell membrane. We can see if you're looking at just the general concentration, we have a high concentration of solute inside and a low concentration of solute outside the cell. So we have a concentration gradient here. According to what we know, that means that these purple molecules are going to want to move out. Now keep in mind, if you have solute differences in concentration, that means you also have a water difference in concentration. So let's just pretend that the inside here has 40% of the purple molecule. And that means the remaining 60% is water. Let's pretend that out here we have 10% of the purple molecule and we have 90% water. So we have a gradient in the purple molecule, 10% versus 40%. So which means it's going to want to go from high to low. And we have a gradient in water. So we have 90% of water outside, 60% of water inside. So that means water is going to want to move in, hence this arrow right here. So the solute wants to move out and the water wants to move in. This is called a hypotonic solution. So hypo means less. And it's talking about less solute outside than inside. So even though we have a difference in water as well, this term is referring to solute. So less solute outside. Another definition is the opposite scenario, where it's hypertonic. So hyper means more. And there's more solute outside. So you can see that there's more of these green molecules outside than inside. So let's just, again, pretend. Let's pretend that we have 50% of the green molecule outside, and we have 50% of water on the outside. On the inside, perhaps this is 15% of the green molecule, and so that means we have 85% water here. So we have more solute outside. So more solute outside is hypertonic. So what does that mean? Now, that means that this, the green molecule wants to move in. So it wants to move in because it's a 50% versus 15%, and it's going from high to low. Now, can it move in? Who knows? Depends what it is. If it's something that's charged. So they say this is salt. Salt can't move in because salt is charged. Salt is NaCl, and when it's dissolved in water, it makes ions, which cannot cross. So they are small, but because they have full charges, they can't cross the cell membrane. So the solute wants to move in, but whether or not it can move in depends on what it is. If it's glucose, sugar, yeah, it can move in. If it's oxygen, yeah, it can move in. If it's carbon dioxide, yeah, it can move in. If it's like a large protein, no, it can't move in because it's too big. So it wants to move in, but we don't know whether or not it can just from this picture. The other thing we have to consider is our water. We have 50% water outside and 85% water inside. Again, it's going to move from high to low, so that means water is going to move out. Water can always move across the cell membrane. It just does so slowly. Last definition is isotonic, and this is basically the same thing as equilibrium. So in this picture here, we have even amounts of the green solute inside and out, and thus even amounts of water inside and out. So what you're going to see is that there's not going to be a whole lot of movement. So the solute doesn't want to move in versus moving out. The water doesn't want to move in versus moving out. So this is equilibrium. So iso means equal. So here's kind of an overview of what I've talked about. So here is our lipid bilayer we're seeing right here. And this one actually has protein molecules. So there's protein molecules that are right here. So notice that some things are crossing directly through the lipid bilayer right here. This solute is crossing. That means that it must be small and no charge on it. Or it could be water, which has just a small charge here. Things that need extra help to cross may go through a channel protein like this one right here. And this one might be water. So water can cross here, but it's super duper duper slow. Instead, it goes across this channel to get in faster. And then you could also have things like here, like this active transport. This could be like a charged ion. This could be like sodium, for example, right here, that brings things across. So only things that can cross directly like this through the cell membrane are small and non-charged, or water slowly. Everything else has to go through a channel or can't pass at all. So if it's something really big, you just can't even cross. Which makes sense, because if you don't want your nucleus leaving the cell, right? So you don't want that to happen. So that's why large things cannot enter or leave the cell. So what kind of things can cross directly through the lipid bilayer? Things that are small and nonpolar. So small and nonpolar can go through. Things that are slightly charged, like water, for example, can go through, but remember, this goes through slowly. Larger molecules, if it's too big, they can't cross at all, and charged can't cross at all, unless they go over special protein channels. So because of the way the membrane is made up, because we have polar heads on each end, and we have non-polar sections of the tails here in the middle, because of that, the cell membranes will repel polar things, large molecules, and charged molecules. So only things that can go over easily with ease are small and nonpolar. So small and nonpolar. Now water is small, but it is polar. So remember, this goes over slowly. Amino acids can cross over. But large molecules like these right here, why can these not go? Because this is big and this is big. Ions are small, but because it has a full charge, it can't cross over. So an example, oxygen. So oxygen travels in the air is O2. So it's a small molecule. It is nonpolar. Same with CO2. CO2 is small and nonpolar, so it could easily cross in and out over this cell membrane of the capillary right here. Facilitated diffusion. So facilitated diffusion uses a protein channel and kind of acts like a bridge, and it can bring things in or out of the cell. It's passive, so it's going to go where there's more to where there's less. So you're going to see it moving in this direction because it's more to less right here. And they can be larger things. They still have to be able to fit in the channel, right? They still have to be able to fit on the bridge. So, but they can be larger and enter that way, or polar like water, for example. So large polar molecules, why can they not get through? Because it's just too big. If it's too large for the bridge, it's not going to make it across the membrane. All right, and then water. Water, like I said, water will travel here across in between the phospholipid molecules, but it's very slow, which is not ideal. And so cells need to have water. They need to have water for cellular respiration. So they need to have it to make energy. So what do? We have a special channel protein. This special channel protein, and I'm going to talk about the name here in a little bit, it's called an aquaporin. Aqua for water, porin for whole. And this is a way of getting water in and out of a cell quickly. So again, it's going to move down the gradient. So there's going to be more to less. So why do we need aquaporins? Because, like I said, water cells need water, and they need water in order to go through cellular respiration, in order to make energy. So we have to have aquaporins so that they can go across the membrane faster. So these are special channels or bridges that just strictly bring in water to cells. And that's in the notes.